In our last video, we looked at the strategy of greedy algorithms, algorithms that at each stage make a small change or addition to the solution because in the short term it looks as if that's going to make things better. On the other hand, we saw that for some problems, like the traveling salesman problem, this is a terrible approach and often leads us not to the true optimum, not to the best possible solution, but to a local optimum. What do I mean by that? I mean a solution which might be pretty good, and it might have the property that if you make any small change, it gets worse, but meanwhile the actual best solution is somewhere else, possibly very far away in the space of all possible solutions. So we can talk about when greedy algorithms work and when they don't by thinking about the shape of the landscape of all possible solutions. In this metaphor, a local optimum would be, say, a little hill here, but the global optimum is a wonderful mountain peak over there. Now, this idea of a landscape comes up in many branches of complex systems and many different sciences. In ecology, for instance, we talk about the fitness landscape, where we're ranging over all possible genomes or phenotypes of some kind of organism or species, and the height is its fitness, the average number of children that will survive, and so on. In physics, we talk about the energy landscape, where we're ranging over all states that a system could be in, and the height is the energy of those states. Except in physics, things like to settle down to low energies, so we flip the landscape upside down. And in that case, our optima are valleys instead of mountain peaks. This comes up even in game theory, where the height of the landscape could be the payoff for your moves. The only tricky thing about that is that in game theory, it's a two-player process. My moves affect your landscape and vice versa. This happens in evolutionary biology as well, because species co-evolve, and what I do as your prey might affect your landscape as a predator. But let's keep things simple, and let's say we're trying to solve a fixed problem with a fixed landscape, so the map isn't constantly moving around as we're trying to explore it. Okay, so some problems have a very simple landscape, what we like to call a Mount Fuji landscape, a term which goes back to the days of genetic algorithms. Genetic algorithms are algorithms which are biologically inspired. They start with some potential solution to a problem, and then they perform mutations, just like evolution does, and try to explore small changes to that solution, finding, nearby things on the landscape, and then if some of those small changes are better, have a higher fitness, they walk upwards. Of course, genetic algorithms also use crossover, like sexual reproduction, but let's focus for now just on this idea of trying small mutations and seeing where that gets us. Well, the nice thing about Mount Fuji is that there's one big peak. So no matter where you start, if at each step you just walk upwards, make some improvement somehow, you can rely on the fact that you will eventually reach the summit. There's no danger that you'll get stuck somewhere. On the other hand, for a lot of computational problems, the situation looks a lot more like the Rockies than like Mount Fuji, where there are many, many different mountain peaks, and they're very far apart from each other, and there are deep valleys in between them. In this situation, you could easily be stuck at a local optimum and find yourself in a situation where the global optimum is somewhere far away, and in order to get from here to there, you would have to go deep into a valley, making your solution much worse before it gets much better. So in that situation, you would really be stuck. You know that, or you might know, or you might guess, that you haven't found the best possible solution. But you have to make a large change to your solution in order to get there. And of course, there's an astronomical number of large changes you could make. It's worse than that. In this picture, well, the map of the Rockies is like 2 or 3 dimensional, but actually this would be more like n-dimensional. And on top of that, you can't see anything. You're lost in a fog because you don't have a map. You have no idea what the global landscape looks like. you're going to have to search or explore it somehow. And in that situation, it's hard to imagine how we can do better than exhaustive search. Now, there's an interesting fact about this landscape, though, because when we define the landscape, it's not just the altitude, the quality of the solution we need to define. We also need to define the topography, or what a mathematician would call the topology. What defines the neighborhood relationships? When is one solution close to another solution? Well, that means asking what types of moves, what types of mutations am I allowed to make? And that depends a little bit on the algorithm. So let me show you a case where we're actually able to turn a complicated Rockies-like landscape into a much simpler Mount Fuji-like one by slightly expanding the set of moves that the algorithm is allowed to make. This is another classic problem in network flow and network design. It comes up in the study of congestion in road networks. It's often used as a game theory problem where people are trying to choose different routes through a network and they're interfering with each other. It's called max flow. We have a directed graph or a directed network where each edge has an arrow on it telling us which way you can go. We have two special nodes or vertices in this network, the source, S, and the destination, T. And on top of that, each of the edges in the network has a capacity, an amount of flow that it can handle. Now, let's assume that these capacities are integers. And I'm going to assume, for instance, that these are the number of available seats on trains or airplanes that we can use to get from S to T. So the max flow problem takes as input this setup, this weighted directed network. And the question is, what is the maximum amount of flow from S to T, which you can think of as the maximum number of students that can get from their university at S to a conference at T using these empty seats. So suppose you're trying to solve this problem. Suppose I'm trying to solve this problem and I have a group of students and I want to send as many as possible to this conference. Well, I might call a travel agent, and I'm happy to tell you that there are still human beings who act as travel agents to arrange this sort of thing. It's not all done on the web. Okay, so suppose my travel agent follows a greedy strategy. Every time they perceive that there's a route from S to T some way through this network with some available seats on each step of the route, they'll grab that and buy a ticket for that route. The only problem with this greedy strategy is that if we're not careful about how we do this, because we often have multiple choices, we might get stuck in local optima. So for instance, my travel agent notices that we can get someone from S to T across the top of this network using one each of those two seats on those legs. And then we can send another student across the bottom two edges of the network. And then we could send a student along this zigzag path that uses that middle branch there and uses up its capacity of 1. But now we're stuck. We've used both seats on this link and both seats on that link, and there's no longer a path from S to T which has available seats all along it. But of course you can see the mistake we made. We shouldn't have used that middle branch, that middle leg at all. Instead, we should have simply sent another student across the top and another student across the bottom, and then we would get 4 of our young colleagues there instead of just 3. So having seen this and having noticed that in a large network with n nodes, there could easily be an exponential number of ways to try to arrange these flows, you might worry that this is a hard problem, that it requires an exhaustive search, that it has a bumpy landscape, that it's hard to find the optimum. But in fact, it's not. We just need to slightly expand the moves that we're allowed to do to improve the current solution. So Richard Feynman claimed that positrons, anti-electrons, were just electrons moving backwards in time. And being antimatter, they can cancel electrons out. So perhaps all we need is anti-students moving backwards in time, canceling out regular students along a particular path, hopefully without an enormous explosion and release of gamma rays. So here is the path that we kind of shouldn't have added, this zigzag path. Well, let's add this path to it. What's going on? Well, that middle edge is going against the arrow. That edge in the network actually only lets you go up. This middle edge is going backwards along it. And that backwards edge will cancel out the edge we had before, so that when we add these two things together, we get these two bona fide paths. Then it turns out that if you allow this type of move, you can never get stuck. So by expanding our notion of what solutions are neighbors of what other solutions, by expanding the list of improvements that we're allowed to make, we've reorganized the landscape, brought these sort of mountain peaks closer together and merged them so that now we can never get stuck. We've changed it from the Rockies to Mount Fuji. That lets us solve the max flow problem in polynomial time. But the interesting thing is we don't think this type of reorganization of the landscape is always possible. We think that there are also problems where the landscape is just unavoidably bumpy, and there's no way to get away from that enormous amount of search.